My name is Noam, and I'll be presenting work on deriving bounds and inequality constraints using logical relations among counterfactuals. This is joint work with my advisor, Ilya Shpitser. In our setting, we suppose we have access to two basic objects. The first is the causal graphical model, which shows the direction of causal influence between the observed variables. And the second is the distribution over those observed variables, which are jointly designated by a bold V. We're often concerned with counterfactual random variables. Y parenthetical A denotes the value that Y would have taken if the random variable A had been exogenously set to some little value A. In other words, if we had intervened on A. There are two motivating questions for this work. The first is the identification question. In other words, what can we say about the distributions of counterfactuals given a causal model and the observed data distribution? And the second is about whether the observed data distribution is compatible with the causal model. In other words, whether observed variables with relationships described by the causal model can have the given distribution. The question of exact identification, that is, when can a counterfactual distribution be given as a functional phi of the observed data, is completely solved for hidden variable DAGs by the ID algorithm, but the question of partial identification, which is when can a counterfactual parameter be bounded by functionals of the observed data, is still an open question, though it has been solved for some specific graphs. The compatibility question, if there are no unobserved variables, can easily be answered by checking that certain conditional independence constraints implied by the causal model hold. These are always equality constraints. If some variables are unobserved, in general, for general graphs, there are no sufficient conditions for compatibility known, although there are some necessary conditions that take the form of inequality constraints as designated in the bottom right corner of the slide. Again, this problem is solved for some specific graphs, but not in general. These gaps in our knowledge are very important because in practice, for practical applications, we often have a large amount of unobserved confounding. In such cases, the exact causal quantity of interest may not be identified. We may not be able to get an exact answer, but we still want to be able to extract some information from the observed data. And likewise, the compatibility question is important because we need to be able to know when the observed data falsify the causal model that we have in mind. So I'll introduce the idea behind our approach in the context of the instrumental variable model, which is one of the first models that bounds and inequality constraints were derived for. So we're going to use the classical setting of clinical trial with non-compliance. So Z represents the trial arm assignment, A represents the treatment actually taken, and Y represents outcome. And A and Y are confounded because an individual's choice about which treatment to take may be influenced by latent personality traits that also affect outcome through other means. In this setting, it's easy to see that an event in one world, which is to say under one intervention, can imply an event in another world. So consider the implication statement on the right side of the slide. Suppose we intervene to set a patient's trial arm to the treatment arm, and we observe that they take the treatment and have a positive outcome. Then suppose that we were asked about what would have happened had we intervened directly to make them take the treatment. Because by the model assumption, the trial arm can only affect outcome through the treatment, and they would have taken treatment in both intervention worlds, they must have had the same outcome under both interventions in both worlds. This intuition is captured by the implication statement. The inequality relationship on the bottom of the slide follows because the antecedent of an entailment is a subset of the consequent, and subsets have smaller measure than their supersets. It's helpful because the distribution on the left-hand side of the inequality is exactly identified. The distribution on the right-hand side is not, so we get a lower bound on the unidentified distribution in terms of a functional of the observed data. So a simple strategy we could adopt for using this idea is to go around to each of the worlds in which we intervene on Z to set it to each of the possible values little z, and find the world in which we can obtain the largest possible lower bound on the target of inference. And that works for some cases. For example, in this sequential treatment model, we can obtain bounds on the distribution of the final outcome. So the Y's are outcomes and the A's are treatments. Can obtain bounds on the distribution of the final outcome under intervention on the treatments, even though both outcomes in one of the treatments are confounded. But in general, the simple strategy we just described leaves some information on the table. In our paper, we present an algorithm for using information from many hypothetical worlds to obtain bounds. So in broad strokes, our idea is to partition the event of interest, YA, into sub-events that span multiple worlds. We then derive new bounds on the resulting cross-world events and sum those bounds to obtain a bound on the target. The strategy is summarized in algorithm 1, but it is pretty involved, so please see the paper for details. Now, note that the only characteristics of the IV model that we used to think about this approach is that first, Z cannot affect Y other than through A, and second, the distribution of A and Y after intervention on Z is identified. So it turns out we can apply the approach to any graph that satisfies those conditions, including graphs in which Z, A, and Y are sets of variables rather than singletons. But this is an example in which they're singletons, where Z acts as a generalized instrument for A. This model may be appropriate in the clinical trial setting if some physicians don't randomize the trial arm as they're supposed to, but instead assign it based on preference, and the physicians also affect the treatment and the outcome of the patient. And I think this is quite a useful model because it opens the door to using instruments that are conditionally rather than absolutely randomized. And we can see that even for a simple model with binary random variables, the bounds that we get can be quite complicated. The cross-world events also, cross-world event implication can also imply that two events are contradictory, as shown by the implication statement on the right side of this slide. And that means that the sets of patients who experience those two events under different interventions is disjoint. So we can use this disjunction to bound the sums of densities of sets of events. The intuition is that if two events are contradictory, no portion of the population may be counted twice in their sum. So if the events are in hypothetical worlds that have identified densities, this idea can be translated into inequality constraints on the observed data distribution, which we'll see in a minute. And note that this turns out to be quite similar to the exclusivity graph approach used in Poderini et al. So here is the same model that we looked at earlier, and we can see sort of a subset of the kinds of inequality constraints that we can derive using this approach. So in conclusion, we show how reasoning about the relationships of hypothetical worlds can be used to derive bounds and inequality constraints. These derivations can often be automated, and we have publicly available software to produce these bounds for graphical models. Thank you very much for listening, and please stop by if you have questions.